it might be nice to have it centered over the coordinate plane, as opposed to if this was the coordinate plane, having it way off to here. Because, you know, if you're real far away from the origin, your numbers are going to be really big, they're going to be really small. If you can keep it here, you might be able to see that, for example, these two distances, they're going to be the same, aren't they? We know that about parallelograms. These two distances here are also going to be the same. And if you look at this as A comma B, this point here is going to be what?
B comma A, or negative A.
It's going to be like, yeah, it's going to be like the opposite of B. And it's going to be the opposite of A, isn't it? And that's going to hold true for these as well. So there's, you know, some good things that we can get by just having this in a convenient location. And depending upon the shape that we choose, we put it on the coordinate plane in different places to make it convenient. So for example, you could have something like a square. And you could put the square, like just center it right over the origin. That might be a convenient location. You could also do something like this. Because then the idea of how far you are up on the Y and how far over you are on the X-axis, those are going to be the same distances. So the numbers get really nice to work with. For figures that have lines of symmetry, such as, well, what's something we've been working with that has lines of symmetry? Has more than one line? Rectangles. So you could center a rectangle over this. What's another figure we've been using? Octagons, yeah. Octagons are going to get pretty busy because you got 8 sides. Triangles, yeah, triangles, you know, you could do a lot of things with triangles. You could set them up like this. You might end up setting them up like that, depending upon what kind of a triangle you have. Hexagon. Let's limit our sides though. I don't want to make it too high. How about this one? A kite. Because now you're talking about a distance on one side of the origin. That's the same as the distance on the other. And we know then that that origin is like at the midpoint. So we can do some measuring and proving that something is or is not a kite by knowing these distances here. We can take a look at these diagonal distances, and you might be able to use the idea of those diagonal distances, if you can calculate them, to prove that 4 points that are put onto a grid make up a parallelogram. Or what's the slope of this line across here? That's 0. And the slope of this is 0. And when lines have the same slope, then they're parallel. You have something in your packet that says that. So if this is a parallelogram, what's going to be true about this slope and that slope? They're also going to be the same. They're going to be the same slope. So measuring diagonals, which we can do, you might be able to do that across here as well. Knowing slopes are the same shows that lines are parallel or sides are parallel. If we had a square like this, what is going to be true about the diagonals for any square? Here, I'll draw a better one up here if I can. What's that? They'll be equal in length. What about their intersection? What's unique about that? It creates a triangle over here. 45
degrees.
What's this angle here? This is going to be 90. So if you could determine these 2 points, find the slope between them. Determine these 2 points, find the slope between them. Don't we have some type of a property or a theorem that discusses when lines intersect at a 90-degree angle?
90, 45, 45.
Now, if we took any 2 lines, we had a line here, and we intersected with another line, what's true about their slopes? Those are not the same. Do you have a piece of graph paper? I'm missing one of the whiteboards, aren't I? That's what's wrong. Why in the heck did it go? I was thinking something's wrong in the room. You have a piece of graph paper?
Wouldn't they be like opposites?
No graph paper? Opposites? What do you mean by opposites?
One's going north and one's going sideways.
I'll try to clean that up for you by
I
tomorrow.
don't know what he's doing.
Just put X and Y axes down here. And then anywhere on your graph paper, just sketch a line that has a slope of, how about 4? Put it anywhere. So rise over run's gotta be 4. So now you need to draw a line that has an intersection of 90 degrees. Or the angle at the intersection needs to be 90 degrees. So you just go anywhere along your line.
Is that a 4th up there?
Yeah.
Is that a 4? Yeah, holy crap. You're right, that one won't. Well, it'll all work in the end, but yeah. 4. Ooh. 1, 2, 3, 4, and 1. Is this better, Luke?
Probably.
Yeah, probably so.
Oh, sure. Dang it. Oh.
That was a 4. There's a slope of 4.
My son's favorite meal is corn dogs.
So now all you have to do is just sketch in a line that crosses at a 90-degree angle and count it up and take a look at what the slope is. Use anything, just get a 90-degree angle. Maybe put a triangle on it, or draw a triangle, use a corner of a piece of paper. Use that. And then anywhere along that line, just sketch in the 90-degree angle, and take a look at what the slope is. Here's the slope. Almost. You're missing one word. What's the slope of that line?
Oh, negative.
You need two words to describe it. You need a straight edge, don't you? That's kind of a bummer. You go 1, 2, 3, 4. There you go. This is gotta be your first one right here. Draw it. Now you need to make it at a 90-degree angle. Oops. There it is. So you gotta bring that on, you'll do a better job. Now figure out what is the slope of that. So there's an intersection point, 1, 2, 3, 4. There you go. So what's the slope of your second line?
Or
One.
negative,
Negative 1 over 4?
negative 4, no, what? Yes.
So you go down 1 and come over 4?
Yeah.
So what does that make that slope?
Negative 4?
If you go down 1,
Oh,
so it's the
Yeah,
change in the y
sorry.
over the change in the x. You go down 1 and you go over 4. So when two lines intersect one another at a 90-degree angle, what's the relationship between their slopes?
So negative 1 over that number. Negative reciprocal.
Well, this is a negative number, and a 4 and a 4 are reciprocals, so they're negative reciprocals. So why do I tell you that? Well, if you have a square, and you figure out the slope of this line, and you figure out the slope of this line, to prove that these 4 points, when they're on the coordinate plane, make an actual square, you're gonna find that the slope of this line is the negative reciprocal of the other. That way you can prove they're at a 90-degree angle. So if I was to give you these points, 2, 2, negative 2, 2, negative 2, negative 2, and 2, negative 2. Can you prove that those 4 points make up the vertices of a square?
Yeah.
So the first step that you might take would be to graph it. So you graph, you sketch it out, and you say, there, yeah, it looks like a square. But does that prove? No, you're shaking your head. But if you could find the slope of this line and the slope of this line by using these 4 points, then you should be able to either prove or disprove it being a square by those lines having negative reciprocal slopes. Yes?
Couldn't you prove it a different way? Is, like, do you have to prove it that way?
Yeah, you could. But when you think about the characteristics of a square, what are other characteristics that would make that a square?
They're parallel, they're at each point, between each point, there's
Just
the same length.
pause for a second. So now you gotta find the slope of that line and that line. This line and this line, so now you've proven that they're parallel.
And then you prove that they're the same length between each
You
point.
gotta prove the same length, the same length, the same length, the same length.
That's a square.
So now you're up to 6 calculations. So can you? Yes. But the question is, can you do it efficiently and quickly? And if we know that the diagonals are at a 90-degree angle, and then that we know the distance from the center to each of these is the same length, you might be able to do that more quickly. Or you could say, this distance is equal to this distance, and at a 90-degree angle. Then that'd be done to just 4 calculations. So the idea is to do it as quickly as possible with as few calculations as you're able to. And when you take a look at convenient locations, on page 672, they've got 7 different figures there where they have a kite and some triangles, parallelograms. There's a rhombus in there, rectangles. Actually, no, it's not a rhombus, it's just the parallelogram shown twice. They show the parallelogram, for example, with a center of rotation and then with one of the vertices being at the origin. So when you're asked to create a convenient location, the idea is to place the image onto the coordinate plane so that all the points of the vertices are simple, easy to use numbers. And usually the way to go after that is to look for lines of reflection and lines of rotation, because it makes calculations easier. Oh, both sides. You give it a go.